This is Smarter Cars, a podcast about autonomous vehicles.
This is the finish line. The Stanford racing team has made its way into the history books.
But the most important thing for me is it actually doesn't matter who comes first. It matters that we as a community achieve it.
Early in a technology, a thousand flowers should bloom.
Welcome back to Season 2 of Smarter Cars. This is your host, Michelle Kairouz. In this episode, we talk with Forrest Iandola, the CEO of DeepScale, a company that makes vision and perception software for autonomous vehicles using deep neural nets. Forrest, welcome to the show.
Thank you. Good to be here.
Great. Can you start by telling us what DeepScale does?
Sure. So we make vision and perception software for cars. So what that means is our job is to automatically figure out what's going on around the car that's trying to drive itself. So where are the lanes, where are the other road users, and basically generate a complete environmental model of what's going on right now that we can actually overlay onto a map. So we have all the static and dynamic objects on the road.
Great. So you're building these perception systems for autonomous vehicles. Do your algorithms work with LiDAR or other sensors or just camera data?
We work with all kinds of sensors. So we do a lot with cameras, with LiDAR, with radar, even infrared cameras potentially. Our first product that we've just recently launched, called Carver, focuses on camera-based perception, but we have lots of increasingly advanced efforts in research and development on applying deep neural networks to radar and LiDAR and other sensors as well.
Interesting. And so is it separate? And I know that a lot of autonomous vehicle systems, sort of take the inputs from the different sensors and kind of fuse it together and interpret it. Would your product then incorporate data from different sensors like LiDAR and cameras, or is it kind of a one-at-a-time analysis?
Interesting question. So this is actually a bit of a debate in the autonomous driving community right now. The debate is kind of at what stage of the process to fuse sensor data. Do you want to create a 3D model of the environment using a bunch of sensors and then figure out where the objects are and get semantic meaning from that? That'd be kind of an early fusion approach. Or do you want to have each sensor have its own algorithms? The sensor outputs, a list of objects or a list of 3D shapes, and then you combine those. I think there are actually trade-offs between those two, but our approach actually is able to be compatible with either of those.
I see. Can you give us a little bit of context? Where does your product sit within the larger stack of software that runs an autonomous vehicle?
Sure. So from my perspective, some of the main things that most people think autonomous cars need, which I think are pretty important, are first sensors and processors. That's kind of the hardware that you're running on. Then perception, so taking that sensor data, processing it to figure out what are the contents, what's the semantic meaning. There's also high definition maps, HD maps, which are offline data from past driving. Then there's sort of a series of things that sort of transition from environmental modeling to control. So, you take the mapping and perception, combine that into a 3D chessboard, which some people call an environmental model. Then you want to predict where the objects are going to go. And then you send that all over to a motion planning system, which decides where your car should go and then figures out how to manipulate and control the car to make that happen. So our piece is primarily in the perception area. So we take raw bits and bytes from sensors and figure out what's going on around us.
Great. That's a really helpful description. Zooming out a little, as you kind of describe the autonomous vehicle stack, some people feel that the development of autonomous vehicles is perhaps taking longer than we expected. And I think people get a little bit confused as to, where we are in in general with the state of the technology, and also kind of where are the holdups? Like which pieces of the stack, as you've just described it, are the most challenging, and where are we having trouble kind of getting to a level 4 that really works?
Good question. So I think the first thing is what are really the goals that we have, and being clear about that. So I think level 4 could be full autonomy anywhere from in just one room of a building all the way out to a pretty large, nearly infinite geofenced area. And if it's nearly infinite, it's level 4, I guess. And if it's fully infinite, perhaps it's level 5. But right. I think so much of what we can and can't do in an autonomous but also safe way today depends on how we're scoping the geofenced area, how we're scoping what kinds of driving behaviors, what kinds of conditions we're willing to operate in. And so I think, today we do have autonomous cars on the road, I believe actually generating revenue. If you look at May Mobility or Easy Mile or some of these companies that have autonomous cars with relatively narrow geofenced paths they can go in. I think one of the things that's going to be important going broader than just small areas with autonomous cars will be how can we reduce the cost to map, or if we need to map, a new area. So how can we get ready to drive on a new road that we haven't previously deployed on without breaking the bank?
Right. And one of the things you hear a lot is about the number of edge cases. Like, oh, there are all these edge cases, and even if you're driving in a fully mapped area that the car has driven a zillion times before, what happens when, the crazy unexpected thing, pops out in the middle of the road, or, some combination of events happen that the car hasn't seen before. How do you feel like companies can deal with the edge case problem?
The way I think about edge cases is that if you haven't seen something before, so let's say you're driving down the street and you see an obstacle in the road, perhaps it's some kind of brick and it's a weird shape and it wasn't in the training set, you still are able to use your active sensors, your radar and your LiDAR, as well as depth estimation based on cameras to figure out that there's something there. Now, if you knew that it was a paper bag, you would run it over. But if you don't know what it is, you want to avoid it. So basically, a lot of these edge cases are things where we can handle them, but we drive overly cautiously to deal with them. And then the more those edge cases we can get the software to really understand, the more moderate as opposed to overly cautious our driving can become.
So is that then really a problem around perception?
I think every part of the stack is going to be facing uncertainty and situations that it hasn't seen before. And the real question is whether you're working on a map where you have some type of entity that's just not in your vocabulary of what you put on the map, or whether you're working on motion prediction and you're predicting the motion of an object that you don't know much about. I think these are all areas where if you just crank up the amount of caution you're applying, that can really help trade off, the safety or improve the safety when you're dealing with edge cases.
Right. So it seems like, as we're talking about these autonomous systems, that there are a few different challenges. One is sort of solving for accuracy. And then there are these other challenges, including efficiency, power, compute, and cost. Can you explain these challenges and sort of how it motivates your work at DeepScale?
So one of the big problems that autonomous vehicles are facing right now is, in a variety of different regions, companies have been able to put autonomous vehicles on the road, sometimes with a safety driver, sometimes with no supervision at all, and get good results. But if you look at the hardware that's required to do that, that hardware ends up costing often more than the car. So you can routinely open up the trunk of autonomous car prototypes from the big companies doing this, and you'll see often hundreds of thousands of dollars worth of graphics processors or tensor processing unit type hardware to do particularly the perception and the AI inference. And so that can be $100,000 plus. Then you look at the sensors; those can be $100,000 plus. Now, there's a whole group of companies. I've heard reports as much as 40 or 50 companies working on miniaturizing and reducing cost of LiDAR, which tends to be the most expensive sensor in autonomous cars. And I think that's moving along. But when you look at the computation, those computers in the trunk, that reducing that is a tricky problem. And if we just wait for computers to get cheaper, it's going to take a long time. And there are some aspects of the system, like the memory access or the I/O, that are just hard to make that much more efficient than they are. And so as a result, we've seen this opportunity in how can we rethink the algorithms, in our case, especially for the perception system in the car, to use much less computing resources, to go from potentially kilowatts of servers in the trunk, more than my house ever uses, unless I have the dryer and dishwasher and everything else turned on at the same time, to go from that to something that fits in the palm of your hand, in terms of the scale of a few cell phones. So that, I think, is a big opportunity, and it's one of the things that I think is limiting larger scale rollouts of autonomous vehicles today.
So what is the kind of power and energy use case for a typical autonomous ride service fleet car today? Like, how much are we talking about in terms of the wattage, or however it's best expressed?
Sure. So there's two things that are worth paying attention to about power and energy. So power is in watts, and then energy is in joules. So power is just a constant thing. You draw a certain amount of power. Energy is integrated over time. So a battery's capacity is measured in energy rather than power. So when you look at the power to run, the servers and the sensors on these fully autonomous vehicle prototypes that are on the street, I've heard reports as high as 5 kilowatts worth of power. I routinely hear reports in the 1 to 3 kilowatt range. And for context, the biggest, most power-hungry processors in mass-produced vehicles tend to be, in the 10 or 20 watt range. So that's a couple orders of magnitude down from what these autonomous car prototypes have. And when you transition over to energy and looking at how many kilowatt hours are in your battery pack, when you have the trunk load of servers drawing kilowatts, you end up exhausting that battery pack more quickly. And when you're driving in the city, your battery pack lasts a long time in terms of hours in a day because you're just driving relatively slowly, but then it gets eaten up quickly, and your range gets reduced when you have autonomous driving software and hardware using power as well.
Right. So are the accuracy challenges where companies are trying to get it right and make sure their systems are correctly identifying objects and setting the right path, are the accuracy challenges intertwined with these kind of compute or cost challenges?
So one of the things I've been most excited about is to discover situations where you can reduce the compute a lot without tarnishing the accuracy. So before starting DeepScale, so I guess a little bit of my backstory. So did a PhD at Berkeley, focused on particularly deep learning and artificial intelligence, and we came up with some pretty clever techniques to reduce the resource utilization of deep neural networks. So less processing, less memory, and so forth. And what we found in that process is that often there are cases where you reduce the amount of computation a lot, and if you take away the right piece of the computation, you end up not hurting the accuracy of the system at all. And so those types of situations are the ones that have allowed the product side of DeepScale and building automotive products to jump down on the compute budget by a couple orders of magnitude and still maintain very competitive accuracy and quality of results.
Yeah, so let's talk about that and some of the kind of value proposition of DeepScale. So your product relies on deep neural nets, and can you explain how they differ from other algorithms or other systems out there? Is it primarily the use of more efficient algorithms to lower the energy and other usage?
So I think the rise of deep neural nets over the last, I would say, 5 to 7 years has been mainly the initial goal was all about accuracy. So one of the leading applications of deep neural networks is computer vision, so making sense of things in images. And computer vision as a research field has been around, at least the way I look at it, about 40 or 50 years. And the way computer vision research has tended to work is, some researchers will put out a data set or put together some data that you can train your algorithms on and then test it on. And, you'll get a measure of accuracy from that kind of work. And, accuracies have stagnated many times in the history of computer vision. And for a lot of the time computer vision has existed, it's had very limited practical applications because the accuracy has actually been so poor. And so, it was really around 2012 when some big breakthroughs, getting, factor of 3 lower error rates in computer vision happened as a result of changing to deep neural networks from some of the previous methods. And since then, it's showed no signs of slowing down. Now, on some of those same benchmarks, we're 10 times lower error rate, 10 times fewer errors than we did before deep neural nets, and it's still improving. So I think deep neural nets have largely been a push to increase accuracy, to get accuracies well above a threshold of how good it needs to be to actuate a robot, for example, safely, or to be the perception front end that helps you actuate a robot, at least. And so your second part of your question was what differentiates deep neural nets from other approaches. And aside from the capability of getting very high accuracy, deep neural nets tend to be a more end-to-end approach. So in the past, if you wanted to distinguish between a dog and a cat, a lot of researchers or engineers doing this would sit down and really think about, what are the differences in kind of the shape of the eyes and the nose of a dog versus a cat, and can we make rules about that? And maybe we could sprinkle in a little bit of machine learning to help generate or interpret those rules. But deep neural nets are a pretty different paradigm where you have lots of labeled images of dogs and cats. You create a deep neural net structure, a training approach, and the model just learns what's the difference between a dog and a cat without having to explicitly write down any rules about it. So those are some of the things that have changed with deep neural nets versus previous approaches.
Right. And so that's really helped with the accuracy of perception systems. And in creating DeepScale, it seems like your focus is to take that sort of state-of-the-art, deep neural net accuracy and to try to squeeze it onto a more energy efficient processor. Is that fair?
Yeah, I think that's the area we've pushed the boundary, that pushed the envelope the most, I would say, in terms of the technology.
Mm-hmm. And you guys are doing that through the nature of your algorithms. Is that right?
Yeah, so a little bit about how we do it. We've actually published a few papers that share some of our approaches. Naturally there's some secret sauce as well, but we've I think helped to kind of start the research community down the path of optimizing for resource efficiency and energy efficiency as well as accuracy. So we have published some papers, such as one called Squeeze Net. Another one, which is for object detection, is called Squeeze Det with a D. Mm-hmm. And those papers have been, widely appreciated, I would say, by the research community. They've also led some engineers in the auto industry to find our team and ask, what's the next step after this, and could we use it in a product? And so back to your question about what are the approaches. So at the lowest level, you've got the processor, right? So we don't modify the processor, we don't modify the processing platform, but we do have good relationships with companies who make processors, and sometimes they're they're receptive to our advice on how to improve them, the processors, to better match what deep neural nets need from them. The next level up, I would say, is the implementation. So that's the software, often written in C++ or CUDA or even assembly code, low-level software that runs deep neural networks fast. So it's really fast code to run deep neural nets. We do all that ourselves. So instead of putting TensorFlow or TensorFlow Lite on an embedded platform, which is a pretty good system, TensorFlow is a pretty good system, but we do our own to be able to get even more customization and even more ability to optimize the code. Then the next level up is the deep neural networks themselves. So that's how many layers is your neural net, what are the dimensions of those layers, what kind of mathematics are you putting in those layers, what functions. We design all that from scratch with efficiency as well as accuracy in mind, and we have some somewhat automated approaches to help us do that with less engineering effort, less manual effort. And then above that, we work on developing our own approaches for how to collect the data to train on, how to correctly curate and annotate that data to ensure its quality and that it's optimizing the networks for the right thing. So we do all those different things, but where some of the magic happens as well is being able to jointly optimize them. So we are able to, in a somewhat automated way, explore neural network designs and neural network implementations that can be unique to each problem that we solve, as well as to each processor, each processing platform we run on. And so that kind of full stack approach tends to have some multiplicative benefits in terms of you get a 10x speed up on one and a 10x speed up on another one, and you're actually talking about a multiplicative, 100x improvement. And that translates to using 100x less hardware, potentially.
Great. So let's talk a little bit more specifically about what DeepScale is delivering in terms of products. You mentioned your Carver 21 product that you're offering. Why don't you tell us a little bit about that? Who is the target customer? What kind of systems? Is this for ADAS systems or fully autonomous?
Sure. So Carver 21 is a piece of perception software that we offer to customers at DeepScale. And, we currently have OEMs and tier ones who are working with it. And so our long-term goal and some of the things that we're doing in our research and development efforts span many types of sensors, many types of vehicles, and many different places you could put the sensor on the car. But what Carver is starting with is the forward-facing camera, so figuring out what's going on in front of the car. And Carver can run with just one camera. We can also add more, but we can go as low as just one camera, and we can still figure out what are the objects in front of us. We can figure out the drivable area. We can find the lanes. We can estimate the depth, figure out how far away the objects are, which is something that deep neural nets coupled with cameras can do quite well. So those are some of the main features that go into Carver. And then, in terms of commercialization, we're targeting both driver assistance as well as fully autonomous driving applications. We think Carver is sufficient to be a major piece, and in some cases even the only piece of the forward-facing perception system for vehicles with collision avoidance software or other safety and convenience features for consumer-owned vehicles. We also see Carver as one of the pieces for helping a fully autonomous vehicle to understand its environment. Great.
So are there other ADAS systems out there that are using deep neural nets today?
People are pretty secretive about this, so it's hard to be sure what's behind the scenes. Yeah. And what I can say is, I think on the driver assistance and consumer vehicle safety type applications, Mobileye is probably the one that's got the most market share that really helped start this industry. I think we're all indebted to them for what they've done so far. I think one challenge is, and I guess I don't know how much Mobileye uses deep neural nets because I haven't seen their internals. But what I can say is Mobileye tends to be kind of an all or nothing solution. So you can either buy a Mobileye device, which has their processor, their choice of camera, their software, and so forth, or you can go find, you can go find someone else and not use Mobileye. So it's not very modular. And so one thing that I think is really something that our customers have found exciting is at DeepScale, you can decide which functionalities to use. So you could use your own lane estimation in conjunction with our capability to figure out where's the drivable area or where are the objects. And you can turn on and off what you need, and the system is modular. It actually consists of multiple neural nets that each do different problems.
Oh, interesting. So customers can choose which pieces of the DeepScale product to use, and it's a little bit plug and play within the larger systems that they might be using.
That's correct. And we're also able to run on processors made by some of the leading automotive silicon companies, as opposed to what you'd find at, say, Mobileye, where you're required to use a Mobileye provided processor over there.
So you're more interoperative in terms of connecting to different hardware.
That's right.
Great. And what is the benefit to customers to outsource the deep neural net piece of it to DeepScale?
I think that the challenge that a lot of people are facing is recruiting AI talent. So I think more broadly at an industry level, deep neural networks as a leading approach, a leading algorithm set within AI, are incredibly powerful. They've only really shown this power in the last 5 or so years through some very groundbreaking work. And I think today there's a relatively limited number of people who really have deep experience in this area. And I know this because I spend a lot of my time personally recruiting these people. And even with the connection to Berkeley and the fact that I was formerly a deep learning researcher, it's still they're few and far between. So I think it's a really tough thing for a company that's in the auto industry, not even kind of traditionally thought of as a software company, much less an AI company, to pull these folks together. I'm sure it could be done, but we're working with a lot of customers who have expertise that's concentrated elsewhere.
Right. So this allows them to focus on the rest of the system and not have to sink a lot of resources into trying to develop the deep neural net piece of it specifically.
That's right. And when I talk to the automakers, and this spans both people working in driver assistance as well as level 4 applications, what I hear over and over again is where these companies really want to differentiate is what use cases they're targeting, what kinds of roads, what kinds of situations, and then also how the car feels. Is it an aggressive driving experience? Is it a more calm and serene driving experience? Is it sporty? Things like that. And so those are areas where you can make the car drive however you want if you're the OEM and you're in charge of the motion planning system and the control system. And no matter how you want the car to drive, you still need most of the same things from the perception system. So there's not a lot of interest, I think, from these customers to have a differentiated solution around perception. They all just want the most precise understanding of the car's environment that they can within a reasonable budget.
Right. And how do you see the space developing for perception? You mentioned earlier the TPUs and that are, there's been some progress there, I think, in terms of compute and efficiency, and those things have been helpful. What do you see coming next? Do there need to be some additional developments either on the hardware or breakthroughs in AI in order to move the industry forward, or is it just a matter of kind of slow progress?
So I think we're all hoping for fast progress, and I think maybe I could unpack that into two questions. So one is, what new things should a perception system ultimately be able to do? Mm-hmm. And then the other question is, what's at stake right now in terms of coming up with different processors and different different implementation platforms. And so if we start out looking at what else perception systems should be able to do, I think one area that's really exciting is how much better could we get at predicting how objects will move. And this motion prediction problem, some companies think of it more as part of the motion planning stack, some think of it more as part of the perception stack. But what's interesting about it is each kind of object that you see moves differently, whether it's a pedestrian, a car, a dog, things like that. Mm-hmm. And there's clues about how it's going to move next. But when it's something with free will, like a person or an animal or a driver, there's only so much that you can predict. And so I think sort of the baseline approach to motion prediction is take each object, look at how it's currently moving, like what's its current motion vector, and just extrapolate that. And you'll look at the results of that and potentially feel good because most of the time vehicles do just continue on their current path, and you'll get a kind of high accuracy score. But it doesn't actually, it doesn't know as much as it looks like it knows, right? The car's going to stop, even if the brake lights are on. That kind of extrapolation won't help you. And so I think today I see a lot of commercial research as well as academic research on this motion prediction problem, but most of these solutions are very narrow. So there will be somebody who writes a paper on how do I predict the motion of cars on a particular highway, on a particular section of I-80 that we've put lots of sensors on just for this experiment. Or how do we predict the motion of pedestrians at crosswalks, or maybe even at a particular crosswalk we were able to generate a data set for. So people are solving these very narrow problems. It's kind of like how computer vision was 20 years ago, where people were solving very narrow problems and even struggling with that. And what I'm expecting will ultimately happen is through a combination of more data and discovering how to apply deep neural nets or other end-to-end learning strategies to motion prediction, we will eventually have one unified approach for motion prediction. So you have a list of objects, you'll have a picture of what the objects look like, you'll have their history and how they've been moving, you'll feed that into some sort of artificial intelligence model, which may be a deep neural net, and it will predict how all the objects will move in the future. And this is an area that really has not been widely discussed in the research or engineering community, and I think it's a huge opportunity to make cars even safer.
Great.
Yeah, so that's kind of what's next. One of the things that I think is the next challenge for perception. On the processing side, I think you were asking, there are better TPUs coming out, what are the implications of that? I think one trend that's kind of interesting is there's certainly progress going on in improving processors to do better, to get more results, to compute more results in a given budget in artificial intelligence specifically. But one other trend is sensor resolution is also increasing. So 4K and even 8K cameras are getting quite cheap, even at high frame rates. Pretty cheap cell phones now have 4K cameras that run at up to 60 frames per second, which is a ton of data. And you sprinkle those around the periphery of a car, on all the corners and all the faces of a car, and you have way more data than people are currently able to deal with, even with the servers in the trunk. And LiDAR trade-offs between resolution and cost are improving, I think, quickly. Radar shows signs of going from a relatively low-resolution sensor to potentially a high-resolution radar-based imager. And so I think it could easily happen that the amount of data you're sifting through increases faster than the speed at which processors are getting better.
Oh, that's really interesting. And then you mentioned earlier the question of memory. Is it true that even if you had sufficient TPUs to manage the data, that you can't really fix the efficiency problem just with TPUs, that there's some issues around memory and other aspects to the system that are limiters? Exactly.
Yeah, I've been a bit of a canary in the coal mine for that one myself. So I've been observing how much better people are making TPUs versus previous hardware. And it's really impressive. I mean, there are lots of people who are claiming a factor of 10 or even more better computational performance per unit of power by going to TPUs. or developing new kinds of TPUs. In fact, a lot of these are even starting to trickle into consumer devices. So you can even get even fairly unknown or not so well-known brands like Huawei have silicon that you can get in a smartphone that does 2 tera operations per second with an onboard TPU. And 2 tera operations per second is where NVIDIA's, just their previous embedded chip, the TX2 was approximately. So, TPUs are there's lots of them coming out and they're going down market, which is great. But one of the challenges, if you look at one of the Huawei phones, for example, that has the 2 tera operation per second TPU in it, it still has basically the same kind of memory that we had last year. And if you can't serve the TPU with enough bytes, with enough data, you end up starving the TPU for work. And so what we're seeing is TPUs are potentially, if you look at what's happened so far and extrapolate a bit, they've already improved things by a factor of at least 10. They'll probably do that again in the next few years. But memory only gets twice as fast every 4 years per unit of energy. So that's a big gap. So every time the TPUs get way better and the memory gets a little bit better, you keep moving further and further towards where I think we're going to land, which is eventually we'll start thinking of computation as being basically free, and we'll think of memory as the limiting factor. And so we'll start optimizing our algorithms to use as little memory traffic as possible. And that's something we've actually already begun to undertake at DeepScale to deal with the current and future hardware and its constraints.
Interesting. So, final question. Tell us what the next few years look like for DeepScale. What are your goals? What is the growth you're anticipating? What kinds of products are you looking to put out in moving forward?
So very long term, we'd love it if our software were in practically every car, maybe even practically every vehicle with wheels that needs to understand its environment. And we would do that partially by having great systems, but also partially by being at a very attractive point in terms of our cost as well as the cost of the hardware that we require. So over the next few years, I'm hoping to be able to point to more and more vehicles in showrooms of vehicles you can actually buy that use DeepScale software for partially or fully autonomous driving, or to support partially or fully autonomous driving with our perception stack. I'm also excited to continue contributing to research in deep neural networks and autonomous driving, and keep innovating and keep advancing what's possible.
And how many employees do you have now, and are you looking to grow?
We have about 35 people right now, mostly in engineering, and yeah, we're definitely continuing to hire aggressively. I feel that the balance of power or balance of requirements have changed a bit. So it used to be that you'd work really hard to come up with a good idea and you just hire a bunch of people to build it. Now I think there's a potentially unbounded number of ideas that are possible with deep learning, but then you have to work super hard to get the right team together who are able to execute on that. So that's something I'm personally spending a lot of time on is meeting those talented people and working to recruit them.
I can imagine. Great. Well, thanks so much for taking the time to come on the podcast. Really appreciate it.
Thank you. This was fun.
All right. Take care. Thanks again to Forrest for joining us. If you're enjoying the show, please leave us a review on Apple Podcasts or wherever you listen to your podcasts. For our show notes for this episode and all of our episodes, please check out our Medium publication called Smarter Cars. Thanks again for listening. We'll see you next time.